Alright, so this is chapter 6. Okay? If you are wondering what happened to chapter 5, we will go to chapter 5 later. We are not going to forget about chapter 5. We'll go to chapter 6. So this is about solar radiation. We are trying to figure out in this chapter, this is the fundamental of solar energy. We need to know where is the sun, how long is the day, how much energy will end up hitting our roof. Now what we're going to do with this with the roof, that will be next week and the week after that. Whether we're going to put a solar heater or going to put a PV panel, that would be later. But for now, we just want to figure out how much is coming on the roof and how much is coming on the south facing roof compared to the north facing roof compared to the east or the west, tilted, flat. Alright, so this is the incident radiation that we have, and the units of the units over here, this is kilowatt hour per meter square per day. So during the whole day, if you have 1 meter square on your roof, how many kilowatt hour he will get? Okay, you multiply this number by 11 cents, and that's how many dollars per day are falling on your roof. You are not using it. All right. So in Oklahoma, in Tulsa, I would say we are getting what, like 4? We are getting 4 kilowatt hour per meter square per day. So figure out how large is the roof in your ceiling, in your house, how many meters square, and multiply this by 4, multiply by this by 11 cents, and that's how many dollars are raining from the sky every day on your roof.
You can't sell it back.
You cannot sell it back, but you can generate the energy and don't buy from the grid. That's how you make the money, basically. If the neighbor wanna buy, yeah. But again, the reason why people buy from the grid and the reason why you wanna be connected to the grid is that insurance. You know that it's always gonna be there. The sun is not gonna always be there. You're gonna have a day when it's like really very so actually this is, I want to show you this, like look at this. In Tulsa we get 4, Oklahoma City we get 4.5, the Panhandle we get 5, and you go there and we get the 8 and stuff in California and Nevada. And the first question is why? I could understand why Alaska. Look at Alaska. Alaska is getting what? 1. So Alaska, I can understand why Alaska is so blue, because it's so far, the sun radiation will be tilted. Sure, Alaska doesn't have enough, but why in Tulsa, Oklahoma, we are less than New Mexico? Why? What's the big deal? Like we are the same latitude, right? Clouds cover, exactly. Clouds cover, and so this is including basically the rains and the clouds and the stuff, and so that's why you put solar panel in Arizona or New Mexico, and you get your money very quickly, right? Because you can see they're getting almost double what we get. All right, very good. So this is, and by the way, this is something called the concentrating solar resource. What's concentrating solar resource? When the sun hits us, you get the direct radiation. They call it the beam radiation, and that's the one that you put your hand and that will cast shadow. But when you put your hand and you cast shadow behind you, it's not going to be totally dark. There's still light, and that light comes from the dome, that hemisphere on top of us. That basically sends radiation. The part that's coming from the dome, that's called diffuse radiation. And the part that's coming directly from the sun, that's the direct radiation. And if you're wondering, well, what is the big deal and why would we divide them? That at the end of the day, my roof will get the radiation anyway, whether it's direct or diffuse. Like if I put my clothes to dry on the roof, it will get benefit from both direct and diffuse. But if you are doing this, what is this? That's the cover of our textbook, right? And for the video, this. So will this work with diffuse radiation? What is that? Mirrors everywhere, sending the beam directly to the furnace. Okay, that is the furnace. That guy that's super white is super white because he's super hot. All those mirrors collect the radiation and send it to that place to make it bright white from the heat it is. So will this work with the diffuse radiation? No, it will not, because the angle is not optimized for it. So each one of those guys is optimized so that when the sun is here, tuck, tuck, and go to the first. And the other one is here because tuck, tuck. So every one, that's why they have different angles, so that they all, depending on the position of the sun, they adjust themselves so that they send all the radiation to that furnace. So there is a lot of application that you only benefit from the beam radiation, not the diffuse radiation. Okay, and that's why the distinction. Good. The other split, direct and diffuse, the other split too is the wavelengths at which that radiation is coming to us. Okay, so right now the standard is called one sun. So when you buy solar panel and they tell you that solar panel is going to give you 300 megawatt, when will it give you 300 megawatt? When will the wind turbine generate the 2.5 megawatt only at the rated speed? So when the solar panel have the sticker of 300 megawatt or 150 megawatt, that's only when it gets one sun. One sun. What is one sun? 1000 watt per meter square. Okay? 1000 watt per meter square. And there's another number that I'm going to tell you later too. A mass has to be 1.5. So that one sun, 1000 watt per meter square or 1 kilowatt per meter square, every meter square should get one sun basically, come with a lot of wavelengths. Okay, so that dotted line over here, the dotted line is the black body radiation at 5800 Kelvin. If the sun was a black body at 5800, it would give that radiation. Well, the sun is actually this guy, the guy that is almost a little bit smaller than the dot line. So our sun really behave as if it's a black body at 5800 Kelvin. Okay, and those splits is basically because of the absorption of the sun atmosphere itself. So that's what the sun will give you, and down on the Earth's surface, this is what we get. Okay, so the reduction between what's available from the sun and what arrived to us in Tulsa, Oklahoma is why the shift, why the drop? CO3, O2, H2O, what are those? The atmosphere. This is the absorption of the atmosphere, and some of them we are really lucky that is being absorbed, because otherwise we'll all get skin cancer, right? The ultraviolet, we wouldn't survive. So we are lucky that the sun, the Earth's atmosphere absorbed a bunch of those things, right? And so this is basically what we get. All right. So now this, what we get, the part that we see is only this. This eye, I'm trying to plot an eye over here, and this is the visible radiation. So this is what we get. And everything above this, all that long tail, that's infrared. And everything here is ultraviolet. Okay? So our eyes don't see this, the infrared, but other animals see this, for example. And our car glass see this. Our car glass not only see this, our car glass trap this. So that's why the car get very hot in the summer. Why? Because everything, basically everything coming from the sun get in, but when the seats become hot and the steering wheel becomes super hot and they want to radiate back, the glass wouldn't let them. Why? Because the glass block the infrared, basically. So you need to be really, really hot so that your radiation become in here, then you can go through the glass. right? So that's why the glass can work as an insulator for radiation. That's why all solar heaters, you usually see them having a glass cover. Okay, and that glass cover is enough to trap the heat inside the water heater. Just like our window in the car trap the heat inside the car and make it very hot for us in the summer. Of course, nicer car, you know, will put very expensive glass that basically can make it a little bit easier for radiation to leave. Okay, and wouldn't act like regular glass where basically, no, you're trapped, you don't get out, let's burn this seat alive, basically. Alright? So it's important to understand that distinction, because this also will explain to you later why the efficiency of the PV panel that generate electricity, what do you think the efficiency is? Give me a number. Yeah, that's not a bad number. 15%. Maximum possible in the lab is like 45 or something. But in the one that you buy from Walmart and Lowe's are gonna be like 15 something. Why? It has to do with that spectrum. That the light we come is not at the same wavelengths. It come at different wavelengths. Okay? So what I'm trying to say also is that when things get hotter, they shift toward this way. So if I put one of you on fire and we start burning him, he will become red, and then he will become, like if we increase the heat, he will become white. He will glow in white. That's how they can tell the steel temperature in furnaces, just by looking at the color. If the steel is like a little bit hot, he will be red. Is really, really hot, he become yellow, right? Really, really hot, he can become white. So the shift, the peak where the radiation come, shift toward the ultraviolet as you get hotter and hotter and hotter. And that's how also they can tell the stars, just by looking at their color. Okay? Very good. So now, the important part of this section or this chapter is to find out exactly where is the sun. Why? Because this is how you can write the program for those mirrors. This is also how you can decide to optimize the solar PV panel in the highway. Which angle should we put? Like if you go drive on the highway and you find those solar panels basically powering the sign up sheets things that they put, they are usually always at the same angle, facing, did you notice, facing what? Facing south. If you watch them when you're driving tomorrow, you will see that they are facing south at a fixed tilt. We'll try to find out what is the best tilt and why they are facing south. So here, this is how to find out where is the sun in the sky, and the sky look like half a sphere as far as we are concerned. You need two angles. This is like you are in a Navy ship and you are shooting an airplane. You just need two angles to find out where the airplane, right? You need this and you need this, right? So this is the solar azimuth angle, and we actually measure it from the south. So if it's coming from the south, that's 0 azimuth angle, right? If it's coming exactly from the east, that's minus 90. If it's coming from the west, that's plus 90. Okay, that's the solar azimuth angle. Now, how high you are from the ground level, this is the solar altitude angle, and we'll give it the symbol alpha. So A for azimuth, alpha for solar altitude angle. And so facing south, your solar azimuth angle, if the sun is coming from south, the solar azimuth angle is 0. You can also use the same notation, and they do, for buildings and PV panels and anything. If the building is also facing south, looking at the south, his azimuth angle is, we'll give it the symbol not AS, we'll just give it the symbol A. So the buildings or the PV panel azimuth angle is A. The sun azimuth angle is AS. S for sun. Okay? And same notation. If the building is facing south, that's basically 0. East minus 90, west plus 90. How about north? What is the angle, azimuth angle for a building facing north, or a PV panel facing north? 180 or minus 180, doesn't matter, right? Very good. So over here he's saying the sun will come from, sun will rise from, yeah, it only rises from the east actually 2 days per year. Exactly east. The sun rises exactly from the east at 90 degree only 2 days per year. Everywhere in the world. And that is basically March 21st and September, right? So if on those 2 days, everywhere in the world, no matter where you live, in Alaska, Tulsa, Rio de Janeiro, the sun will rise exactly from the east. So if you want to know where is your east exactly, look up March 21st, find out where is the sun, that is the east. Okay? Meanwhile, so there is this like 2 points, right? And they separate the summer season and the winter season. So from March 21st until September 23rd, that's basically summer. And from September 23rd all the way to March, that's winter. So during the whole summer thing, the sun will rise from here. What's that? Northeast. Okay? Or east-north. Basically, it rises a little bit earlier, a little bit behind our back. And it go up mid-noon or noon, it will come in the middle and south and then fall down again. And it's symmetric across that orbit. In the winter, which is the winter from September 21st, 23rd all the way to December, all the way to March 21st, the sun will rise a little bit from the south, not exactly east. And it will also rise a little bit later, not exactly at 6. So this one, it will rise at 6 a.m. and fall 6 p.m. True. I'll prove it to you in a minute. But then during the winter, the sun will come later, right? And the day is shorter. Noon, it's facing south, and then it fall down again, exactly at the mirror image from where it came from. If it came from 10 degrees to the east, it will fall down 10 degrees to the west on the other side. Okay? The equation that describe those two angles, alpha and AS, we're gonna use them to calculate where is the sun at any point. Here are the two equations. Okay? And we have them in our book. And let's see what those equations. So the typical problem would be, where is the sun in Tulsa, Oklahoma, April 1st at 10 a.m. Where is the sun? Find the sun for me. If you know that, and we have a solar thermal power plant, you can adjust the mirror of each one of them by basically pointing it to the sun, between the sun and between the tower. They are electronically corrected, not mechanically. They move all the time. They have to move to track the sun. And so we need to know what is the equation that controls them. Okay, and that is the equation to calculate alpha and AS. So sine alpha. And so once you find sine alpha, you get alpha by doing sine minus 1, right? Sine minus 1 is not 1 over sine, right? It's like you do the arc sine. It's sine L, sine delta plus cosine L, cosine delta, cosine HS. There are three angles here that will calculate alpha for you. The L, that's the easiest one. That's the latitude. What's your latitude? It's the location where you are, the circle where you are sitting in. So if you are living on the equator, your latitude is 0. When you are sitting in the North Pole, your latitude is 90, plus 90. If you are living in Tulsa, Oklahoma, your latitude is, yes, how much? 36. Right? So in Tulsa, Oklahoma, we have latitude 36. So that's the L. Here's sine L and here's cosine L. Okay? Now, the HS is called the solar hour angle. And this is the most confusing. So let's wake up, because you are sleeping. What is the hour angle? It's the time from noon expressed in angles. What does that mean? What is your time right now? Let's call it 11 a.m. So how far you are from noon? I still have 1 hour to hit the noon. Every hour is 15 degrees. So your hour angle is minus 15. At 10 a.m. the hour angle is minus 30. 2 p.m. the hour angle is, that's 2 hour afternoon. Every hour is 15 degree, then it is 30, right? So why every hour is 15 degree? Because the earth rotates around itself 360 degree in 24 hours. So 360 degree over 24 is 15. So basically the earth rotates 15 degree every hour, right? Every hour you move 15 degree from where you are. So that is our angle. It's the time expressed in degrees. Very good. Now the delta S is the date, the day of the year expressed in an angle. We'll see the equation for it. So then what I'm saying is that then this equation will tell you for any place, latitude, Tulsa, Los Angeles, New York, for any day, delta S, I didn't show you the equation yet, and for any time. Knowing the day, time, and location, you can find the alpha. And the same thing for the azimuth angle, AS. It's the same thing. Delta S, H, and alpha, which is basically here. Correct? So now let's find out what's the delta S, how we turn the date into an angle. So the official name for the delta S is the solar declination angle, and it comes from this graph. So if you know the day of the year, you can come to this graph and find out this angle. It's also this equation, and so the equation is easier actually, because the graph is hard to read. So the equation say delta S is 23.45 sine 360 to 84 plus n over 365. And what's n? That is the order of the day in the year. They call it the Julian day. So for January 1, the n is 1. January 31st, the n is 31st. February 1, n is 32. December 31st is 365. So when I say May 4th, then you have to basically add 31st plus 31 for January, 28 for February. We don't have 29 in this course, so all our February is 28. Plus 31st for March, plus 30 for April, plus, right, May the 5th? Or May the 4th, right? So you plus 4 for May. You got it? So now what is this angle exactly? Okay, I understand that you can turn the n into an angle by this equation. It has a meaning, and that is the, in this sketch, that is the delta. That is the solar declination angle. Okay, what is that exactly you're plotting here? That's the equatorial plane. That's the circle dividing the Earth into half. And that circle, with the line connecting the center of the Earth to the center of the Sun, is making that declination angle. So now, why does this angle change during the seasons, and it go from 0, it go from minus 23.45 to plus 23.45. Okay, and it does this in the middle of the summer, it become plus 23, and it's minus in the middle of the winter. Okay, so why does it change? So notice that the Earth's angle, or the Earth's axis, does not really wobble in our lifetime. Like really long time ago, maybe he did. He did long time ago. But as far as we are concerned, I will retire, you guys will retire, your grandchildren will retire, and it will stay at this angle. Okay, so the textbook is valid for like bunch of generation. We are fine with 23.45. So that x is not gonna change. Okay, the Earth rotates around it and it's like this, but the Earth move around the Sun. So if someone standing on the Sun in the middle of the summer, he will see, wow, the Earth is rotating, like pointing toward me. If I try to measure this angle, it's plus 23. But come the winter, you will like, wow, why the Earth is like giving me its back, basically. It's like tilting forward, away from me. And if you try to measure that angle, with the equatorial plane now tilted like this, it will become minus 23.45. And so this is summer, here is the sun, and this is the Earth's X. Summer, winter, and here, that's basically fall and spring. And if you try to imagine the equatorial plane, yes, he's tilted like this, but the line coming from the sun will go straight through that equatorial plane, and the angle would be 0. Right? So for that guy sitting on the sun looking at the Earth, he will actually notice that the Earth kind of like really wobbling back and forth toward him. Come toward him in the summer, away from him in the winter, and in the spring it feels to him that, well, the equatorial plane is fixed basically. Does this make sense? Point is, now we have the date through delta S, we have the time through the hour angle, and we have the location through L. And you can go use this equation and find out exactly where is the sun, every place, any time, any day. And so it will be very clear to you then that in specifically the spring 21st and September, what happened to delta S? Delta S would be 0, right? And if you try to find out when alpha would be 0, that is the kind of the sunrise. Alpha is 0, that's the sunrise, right? Alpha is 90 degree, what is that? If alpha is 90 degree, sun is like in the zenith of the sky. Your shadow will be under you. That's what alpha is 90 mean. Alpha 0, that is basically the sunrise. But officially, or really, sunrise does not happen at alpha equals 0. The sunrise happens at alpha. Excellent. Excellent. Not plus something, negative something. Because of the curvature and the radiation hitting the sky, reflecting back, you get the apparent sunrise will be a little bit negative. But anyway, so if you calculate alpha equals 0, you will find out that it's happening everywhere, no matter what's the L, at 6 a.m. Our angle 6 a.m. What is the hour angle for 6 a.m.? 15 degree for every hour, 6 hour. So 15 times 6 is 90, minus 90. You'll find out that sunrise, no matter what the L is, when you give this delta equals 0, it will happen at 6 a.m. Okay? And more interestingly, AS, where does the sun come from when alpha was 0? The location for sunrise. That will also, no matter where the L is, it will always happen at east, exactly.
So is this how they get official sunrise and sunset?
So by official, if you mean the calculation that come in the calendars, again the sunrise will actually happen a little bit negative. Right? Like the light, you will see the light in the sky will come a little bit when alpha is still negative something. Right? But this equation will tell you exactly when alpha is 0. And those chart that we're going to see today is going to be for alpha equals 0. Exactly. Alright? Remember, we really care about the direct radiation too. It's not just the diffuse. I mean, we don't really, and as far as solar radiation is concerned, we don't care a little bit of sparkling light. We really need the full power. We need one sun to get the 300 megawatt that the stickers say on our PV panel. So we don't really care about those tiny things at the beginning. So using those two equations, you can plot alpha against AS, and it will be something like this. Okay, so negative AM, that's the azimuth angle, minus 120. Look at this. That must be deep what? Deep summer. When it comes minus 120, not 90, minus 120, the sun is coming from almost north, right? And it's coming at what time? 5 a.m. Okay? And so yeah, that's June 21st, right, for Mississippi. June 21st, that's like really summer for them. So 5 a.m., you go all the way until you hit solar noon, and then fall down exactly symmetric. 5 a.m., 7 p.m. Coming at minus 120, fall down at 120. Okay?